Yeah. The last class we discussed about two CUDA codes, right? That is dot product of two vectors and multiplication of matrices. Do you have any problem while understanding those programs?
Sir, codes not uploaded.
Oh, okay. And most probably I will upload it by today evening.
Okay.
Okay, right. As long as the explanation is concerned, do you have any problem or do you have any doubts? I'm here to clarify your doubts.
No, sir.
Okay, right. In this class, actually, I would like to discuss that particular same problem by considering how can we calculate dot product of two vectors by using the concept of shared memory. Next one, suppose if you want to measure the execution time of a kernel, how can we measure the execution time of the kernel by using the concept of events? Next one, suppose if you want to execute overlapping of kernels on a particular GPU card by using the concept of streams. Okay, how can we do that? So in this session, I would like to discuss on, I'm going to discuss on how to use shared memory and how can we use the events and how can we use this particular streams concept. Okay, first one. Here, when we look at this particular vector dot product, that means in the vector dot product, what are you going to do? We are going to calculate dot product of two vectors. Dot product of two vectors is a simple scalar value. In the last class, I discussed about this particular logic, right? With the help of this particular logic, we can calculate the dot product. Later, we are going to pass that particular value, some value to the host program. With the help of that host program, we are going to print it, right? Are you with me? Are you with me?
Yes, sir.
Yeah. Uh, Here point is when we look at this particular one, uh, we can find the dot product of two vectors by using the concept of heterogeneous computing. What is heterogeneous computing? Okay. Nowadays, you can heard the term heterogeneous computing. When you look at the term heterogeneous computing, part of the execution can be done by using GPUs, and part of the execution can be done by using CPUs. After that, we can combine both the results and we can generate the result for the given problem. Okay, that is heterogeneous computing. Here, I would like to discuss the idea of heterogeneous computing for this particular dot matrix multiplication problem. A reason behind that is you have some idea on how to find the dot matrix of so how to find the dot product of two vectors, right? Fine. Suppose here problem is like this. Suppose if there are two vectors, this is one vector, and this is another vector. Vector A and vector B. Here our objective is we have to find the dot product of these two vectors A and B. Okay. What is with us? We have a one CPU or host, and we have one GPU card, that is device. In the last class, what we did, actually we transferred both A and B vectors to the device. Okay. After that, we computed the result here. Later, we copy back that particular result to the host machine, and we are printing that particular result here, right? That is the one, right? But actually, suppose consider this part scenario. While performing computation on the device, host is free, right? Nowadays, actually, when we look at the laptops or desktops, in the laptops or desktops, you can see the considerable number of cores, right? It is most of the laptops or desktops are 8 cores. or 16 cores. Suppose if you are working on a simple server, okay, server may have a card, right? Suppose in that particular server, we can have 16 cores. Okay, in that context, we can use the cores which are there in that particular host machine also to solve that particular problem, part of the problem. Okay, in that context, what can be done? Suppose if the length of this particular vector is n, right? In that context, we can divide this particular problem into two subproblems. Okay, this subproblem of length n by 2, this subproblem of length n by 2, n by 2, n by 2. We can find the dot product of these two subvectors. We can find the dot product of these two vectors on the device. Okay, and the dot product of these two vectors on the host. Later, we can combine both the results, right? When we add these both the results, we'll get the solution to the original problem. Are you with me? Are you with me?
Yes, sir.
Yeah. In that context, what we have to do? Okay. Yes, problem is similar to the similar problem. Here, what are you going to do? Here, anyhow, we don't need this particular one. Forget about this particular. Okay. Yeah. Here we are allocating for the memory for the both the vectors A and B. After that, we are going to read the values into A and B. Once we read the values into A and B, what can we do? Okay, we have to compute part of it by using GPU and part of it by using CPU. So I would like to divide into two equal parts. Okay, when we look at this CUDA MLOC, what is the size of the memory for this CUDA MLOC? When you look at this particular one, for DA, we are allocating memory space for n by 2 integer units. For DB, we are allocating n by 2 integer units. Okay, that means for half of the problem, we are going to solve it on the device. Okay, after that, so from these two steps, oh, from these two steps, what is our interpretation? Our interpretation is, okay, we are allocating the memory for DA and DB, and size of those size of the each vector is n by 2. The vector on the device is n by 2. Later, what are we doing here? We are copying half of the elements from vector A to dA, and another half of the elements from vector B to dB. Now, device has first n by 2 elements from the both the vectors. Okay. After that, here what are we doing? Here we are calling multiply using GPUs. We are going to perform the multiplication for the first n by 2 elements. For the first n by 2 elements. Are you with me? Are you with me?
Yes, sir.
Is it clear till this particular point? Okay. After that, for the second half, what we have to do? We are going to solve the remaining part of the subproblem by using CPU. Suppose if you want to solve the remaining part of the subproblem by using CPU's host mission, what can be done? We have to consider, okay, simple thing. This is a simple one. What is this? Actually, here, what can you see? For int I equal to n by 2, we are going to consider the second half of the vector. I less than n, I plus plus, temp sum equal to temp sum plus a of I times b of I. This is simple sequential model, right? Nothing great in that. Okay, are you with me? Here we are calculating the dot product for the remaining half. Later, we can think about how can we execute or how can we calculate this particular partial dot product in parallel. Okay. Once we have these two results, what can be done? We have to copy sum that is calculated on the device into this particular sum variable. Later, we are updating that particular sum with sum plus temp sum. Then we'll get the final result. Is it clear? Is it clear?
Yes, sir.
Okay. Yeah, when we look at this particular one, here we solve the part of the problem by using a device, GPU card, and part of it by using CPU. Okay. Yeah. If we solve any problem in this fashion, usually that is called heterogeneous computing. Nothing great in that. Okay. Next, after that, I'm going to print that particular execution times. Now, I would like to print the result. I'm going to execute this particular one. How can I execute any program? NVCC vector product.cu minus O vector.product.o. Okay. After that, vector.product.o size. Here size is 10 power 9. Yeah, size is 10 power 9. And the number of blocks is 10 and threads per block is 100. Threads per block is 100. Let us see. Let us see. Here, what can you see? Actually, dot product of those two vectors is length of the vector. So when you look at this particular test, here we observe the test is passed. That means it is execution result is correct. Next, when we look at this particular problem, here what can you see? Here you can see that device execution time. That means half of the problem, we are going to solve it on the device, and remaining half is going to be solved on the CPU, right? When you look at this particular piece of code, here you can see, what can you see here? Here we are going to execute these statements, okay, on the host machine. When we find the difference between these two, when you find the difference between these two, usually we'll get the execution time on the host machine. All right, are you with me? That means difference between T4 and T5. Difference between T4 and T5 gives the execution time on the host. Okay, that means half of the problem. Next one is when we look at the remaining first half, here when we look at this particular one, here what can you see? Get time of the day here, okay, and get time of the day here. This is the execution time. When we find the difference between these two, okay, what do we get? We will get the execution time on the device. Are you with me? Is it clear? If the difference between TV3 and TV4 gives the execution time on the device, and difference between TV4 and TV5 execution time on the host. Is it clear?
Yes, sir.
Okay. Now here our objective is, okay, when we look at these execution times, what can you see here? Okay, execution time on the device is 0.07 seconds. Okay, execution time on the host is, okay, 1.39 seconds. Okay, Suppose if you are able to reduce this particular execution time on the host mission, we can increase the speed up. We can increase the speed up. Are you with me?
Yes, sir.
Okay. Yeah. In this course, actually, we studied about this OpenMP, right? Shared memory programming. Okay. We are going to solve that particular problem by using shared memory programming. Okay. How can we solve that particular shared memory programming? How can we do that? We are going to, yeah. Here we have some constructs. You know those constructs, right? Those constructs are hash pragma OMP parallel for. Hash pragma OMP parallel for. Here we are performing reduction operation on temp sum. We are performing reduction operation on temp sum. Are you with me? Are you with me?
Yes, sir.
Yeah. Now I'm going to execute this particular piece of code. How can I execute it? Now NVCC. Do you know how to compile? Suppose if you want to execute any OpenMP program, we have to use -f OpenMP, right? We
Yes,
have to
sir.
use the flag. Here we are going to compile X compiler -f OpenMP. Yeah, there are no others. Now I'm going to execute it. Here you can see the difference, right? This execution time, this device execution time is more or less same. Here it is 0.07. Here it is 0.08. When we look at the execution time on the host mission, right? This is the execution time on the host. This is the execution time on the device. Are you with me? Sorry. This is the execution time on the host. This is the execution time on the uh, host, right? You can find the difference between these two execution times. Did you get my point? Earlier it is 1.39 seconds. Here it is 0.17 seconds. In both the cases, result is passed, test is passed, right? Okay, we got the correct result. Okay, but there is a difference in the execution times. Okay, here
So,
what we did
sir,
actually,
NVCC gives instruction for compiler in the GPU.
NVCC generates two types of codes, right? Codes that are going to be executed on the device and codes that are going to be executed on the host. Are you with me? If we
Yes, sir.
use the flag -x compiler FO OpenMP, that means we are going to parallelize the code that is going to be executed on the host machine. Here, we are going to parallelize the code that is going to be executed on the host machine. Are you with me?
So this -x compiler we have to use when in host part. If we use OpenMP, then we have to use this one, or
Yeah, suppose to use OpenMP codes in our host machine or to execute OpenMP codes in our host machine, we have to use that particular compiler flag. NVCC -x compiler hyphen -f OpenMP.
okay.
Okay. Now, not only because of that, we reduce the total execution time, right? Here you can see that. Are you with me? Is there any problem while understanding this particular piece of code? I hope that as of now, you don't have any problem. If you have any problem, please let me know.
Sir, so basically we are by using this dash XM compiler and dash F OpenMP, we are actually parallelizing it on the host, right?
Yeah, we are going to parallelize the code on the host machine.
Okay.
Anyhow, we know how to parallelize. Actually, that particular device code is already it is parallelized, right? Each thread
Yes,
is
yes.
going to be executed independent.
Yes.
Okay. Now,
When we use only normal NVCC, what is the default compiler for the host, sir?
default compiler means usually default compiler is simple GCC compiler.
Okay, so if you
Okay.
are not specifying NVCC, only NVCC,
Yeah,
then
yeah,
for host it will take GCC.
yeah. Usually, no, NVCC is built on the top of GCC, right?
Okay,
Okay, that is why when we compile any program by using NVCC compiler, it is going to generate two executables. Okay, one is which is going to be executed on the host machine, and one is it is going to be executed on the device. Okay. After that, these two executable, what are they going to do? If there are any synchronization points in our code, okay, these two things are going to wait for each other. Okay. If there is no synchronization point, anyhow, we are going to executing from the host mission. Okay. The main thread, actually, suppose a main thread should wait for that particular device thread. Once device thread reaches to this particular main function, we can terminate that particular program.
okay,
Is it
sir.
clear?
Yes, sir.
Yeah. Now, there is an important point here. I would like to explain that particular one. See this. When you look at this particular piece of code, here we considered CUDA device synchronize, right? What is the meaning of CUDA device synchronize? That is a synchronization point for the thread which is going to be executed on the host machine, and for the threads which are going to be executed on the device, right?
Yes, sir.
Okay. That means here main thread is going to wait for the device threads from the device. If threads from the device reach to this particular point, then only main thread will proceed further. Are you with me? When you look at
Yes,
this
sir.
particular problem, how is this problem? Here, actually, total problem size is n. Total problem size is n. We are dividing this particular problem into two sub-problems, each sub-problem of size n by 2 each. N by 2 each. Here, by using GPU, we are going to solve this particular problem by using some number of GPU threads or CUDA cores. Okay. Once this job is done, okay, here this is the main thread. My main thread is going to wait here. Once this job is done, okay, all these threads comes to this particular synchronization point. This is CUDA device synchronize. Okay, from this point onwards, actually what will happen is main thread, that means threads, is going to execute the program, execute that. After that, it reaches the particular parallel loop. Here we are going to solve this particular problem in parallel. Okay. Okay. Later we are going to add result from this one and result plus this one to find the result to the original problem. To find the result to the original problem. That is the scenario. Okay. You get my point?
Yes, sir.
Okay. But actually, when we look at this particular problem, both are independent of each other, because this particular problem, okay, is no way dependent on this particular one. In that context, this problem can be solved during this particular time itself, right? Then we can save the execution time. Are you with me?
Yes, 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 sir.
Okay. So in that context, actually, what we have to do is there is no need to put CUDA device synchronize there. There is no need to put CUDA device synchronize there, right? We can simply remove that CUDA device synchronize from that particular place. Okay. And then that means I'm going to comment that particular one. When I comment that particular one, please see that result. Yeah, I commented that line. When I after commenting that particular line, I'm going to execute the same piece of code. I'm going to compile it, that particular one. Yeah. Here also we got the correct result, right? Here also we got the correct result. Are you with me? Are you with me?
Yes, sir.
Yeah. So that here we can save that particular time, device execution time, right? Okay. So how much amount of time we can save here? Okay, we can save that particular 0. In earlier case, it is 0.08 is there, right? Device execution time. We can save that that particular that much amount of time here, right? Are you with me?
Yes, sir.
Yeah, in that way we can improve the speed up. Suppose whenever there is a need, then only we will put CUDA device synchronizer barriers. Suppose if we unnecessarily put the barriers in our code, our execution is going to be delayed. Our execution is going to be delayed. That is the first takeaway point from this particular one. Is it clear? Is it clear?
Yes, sir.
Okay. After that, here what can you see? Here you can see that device execution time is 0.00034. Here device execution time is 0.083. Earlier one is device execution time is 0.07. That means here there is a problem to measure the execution time on the device. Here there is a problem to measure the execution time on the device. Okay. Are you with me? Are you with me?
Yes,
See,
sir.
yeah, here execution time is this one, and here execution time is that one, that particular one. Okay, which one is the correct? This one is the correct answer, but here we are unable to measure the execution time. Okay, here what we did to measure the execution time, we use the get time of the day. Usually, get time of day is used to measure the execution on the CPU, on the host machine, not on the device. Suppose to measure the execution time on the device, what we have to do is we have to use the concept of we have to use the concept of events or CUDA events. Okay, in CUDA programming, okay, uh, there is a concept of events is there. Okay, usually an event is a synchronization primitive. Okay, with the help of that particular primitive, okay, we can measure uh, actually measure the execution time of particular kernel or execution time of a set of instructions on the device. Okay, so actually in the next program, okay, I would like to explain. I'm going to explain how can we measure execution time of a kernel by using the concept of events. Okay, or CUDA events. Are you with me? So in this CUDA event, okay, in CUDA programming, we are using the concept of events, okay, or CUDA events, okay. Okay, an event is a synchronization primitive that allows us to measure the time taken by a sequence of CUDA operations, okay, sequence of CUDA operations. Suppose we are going to execute some set of operations on the device, okay, we want to measure the execution time of those operations, okay. In that context, we are going to use, we have to use mm, this one, actually, CUDA events. Okay, suppose to measure the execution time, we can put that particular one CUDA device synchronize. With the help of CUDA device synchronize, we can measure it. But that is a blocking statement. When we put CUDA device synchronize, it is going to block the main thread. Okay, without blocking the main thread, we have to measure the execution time on the kernel. How can we measure the execution time of a kernel? Okay, uh, by using the concept of, we can measure the execution time of a kernel by using the concept of CUDA events. Okay. Now, what I'm going to do is, I would like to explain this particular CUDA events by considering the same example, because this problem is familiar to you, right? That is why I would like to consider same one. Okay. vector dot product by using CUDA events. When we look at this particular one, here, what can you see? Okay, yeah, in simple terms, okay, by using CUDA events, okay, we can store in the timestamp, right? When we store the timestamp of the particular device, okay, after executing given kernel, again we are storing the timestamp. We are finding the difference between those two. That nothing great in that. Okay, right. See here, what I did. This is the kernel. Which one is what is the kernel? Kernel is multiply using GPUs. This is the kernel. I want to measure the execution time of this particular kernel. To measure the execution time of this particular kernel, okay, here what I called? I called one function, right? That function is CUDA event record. Okay, I'm going to record timestamp into the variable start. Okay, after that CUDA event record. Okay, after executing that particular kernel, I'm measuring that. I'm going to store the timestamp in this top variable. Okay, when we look at the particular function, we are passing the two arguments. Okay, first one is either start or stop, and second one is zero. Okay, zero is the stream number. Okay, anyhow, while discussing the streams, I will discuss that particular second argument. Okay, here what can you see? By default, we are submitting this particular CUDA kernel to a zeroth stream. Okay, next one. So here we are using these two variables, right? Start and stop. So what we have to do, we have to declare those variables, right? To declare those variables, okay, what we have to do, we have to, where we have to declare, when we look at this simple piece of code, here you can see that, okay, here I declared those those variables, start and stop, okay. These two variables are of type CUDA event. These two variables are of type CUDA event. Okay. Once we declare those variables, after that, what we have to do, we have to create an event. Okay. For those two variables. That means CUDA event create address of start and CUDA event create and stop. Okay. We created these two events. Okay. Once we created those events, after calling that particular CUDA event record, okay, we are going to store the timestamp of that particular uh, device. Okay, whenever we call CUDA event record, okay, we are going to store the particular timestamp into that particular variable. Okay, those variables are of type, okay, CUDA event. Are you with me? Here, when we look at these three statements, here, what can you observe? First, this particular one is to declaring the variables. These two variables are of type CUDA event. After that, we are creating the two events. Okay. After that, we are using those events to measure the timestamps. Okay. We are using with the help of those events, we are recording the timestamp by calling the function CUDA event record. By calling the function CUDA event record. CUDA event. This is CUDA event record. Are you with me? Are you with me?
Yes, sir.
Yeah. Remaining things are very simple and straightforward. Okay, I haven't changed any code at all, right? Okay. Here I consider this particular. Okay, for better understanding, here I also call get time of the day. Suppose if you find the difference between these two, then you will get one answer. When you find the difference between these two, you will get another answer. Okay. Next, after that, to these are the statement to solve the remaining part of the code by using what is that host machine. Is it clear? Any doubt? No, right? Here, what I have to do, I have to add one more thing here. Which statement I have to add it here? Here, I haven't added that particular statement. Here, I have to add one statement, right? What is the statement? Hash, hash, pragma, OMP, parallel for, okay. After that,
Reduce.
reduce or reduction.
Reductions.
Okay. Reduction and which operator? Plus, what is the variable name?
Temp
Temp
sum.
sum. Temp sum. Is it clear? Okay. This is the case. So here, when you find the difference between these two, TB4 and TB5, you will get the execution time on the host machine. If you find the difference between this start and stop, okay, you will get the execution time of the kernel. Okay, by using, suppose if you use CUDA device synchronize, straight away you can get it. Okay, I will show that also, right? Don't worry. Here, what can you see? Here you can see that. Okay, now uh, we recorded those two events, right? By using CUDA event record of stop and CUDA event record of start. Okay, after that, we have to measure the difference between those two timestamps by using CUDA event elapsed function. Here, when we look at this particular one, CUDA event elapsed time, there is a start event and a stop event. We have to find the difference between these two. We are going to store that particular difference into this particular variable elapsed time, into the difference variable elapsed time. Elapsed time, actually elapsed time gives the value in milliseconds. Suppose if you want to print the result in seconds, what we have to do, we have to divide that particular one with 1000. Is it clear? Is it clear? So, suppose if you want to measure the execution time of a kernel, okay, uh, we have to use CUDA events. We have to use CUDA event. Okay. Yeah, CUDA events provide a way to insert the markers into the execution stream. Okay. Once we insert the markers into the the execution stream, when we find the difference between those two markers by using a function called CUDA event elapsed time, we can get the execution time of that particular kernel or stream of instructions that are going to be executed on the device. Is it clear? Or do you have any other doubt? Can I execute this program now?
Yes, sir.
Okay. Now I'm going to execute this particular program. Yeah, here, what is the program name? Vector dot product event, right? Here, output is event. They are successfully compiled. After that, event. Yes. Here, what can you see? Here you can see that, okay, this is the device execution time. Here we use the elapsed time function, right? CUDA event elapsed time function, right? When I use the CUDA event elapsed time execution time on the kernel is 0.01 seconds. Is it clear? If I use get time of the day, this is the value. Okay. This is similar to the previous value. So this result is wrong. That is wrong result, right? Did you get my point? Did you get my point? Yeah.
Yes, sir.
Now, what can I do is, I would like to insert CUDA device synchronize also. In the same piece of code, I would like to introduce CUDA device synchronize. See, here I considered CUDA device synchronize also. CUDA device synchronize, now I remove the comment, right? Now suppose if I execute this particular piece of code, both the values should be more or less same, right? Then only it is correct. That means here when we use the CUDA device synchronize, what is going to be this difference? Okay, difference between TV3 and TV4 and this particular elapsed CUDA event elapsed time. Okay, that function, both the functions will give the correct, more or less correct result. Okay, let us see. Now I'm going to execute this piece of code. What happened? See. Now you can see that this is the device execution time. We measured this particular device execution by considering CUDA device synchronize. This is this particular one, CUDA event elapsed time. These two values more or less same, right? Are you with me? Are you with me? Here there is a
Yes, sir.
big difference, right? That means there is a problem with this approach. There is that result is wrong. Clear? Is it clear?
Yes.
Okay. Next one. Usually, while compiling any C programs, we are going to perform different optimizations, right? We can compile this particular one with different optimization. Suppose if I want to compile this particular code with optimization compiler 3. Yeah, I successfully compiled. Now I'm executing this one. See, if I do this particular compiler optimization, okay, without doing anything, okay, I can reduce the execution time, right? Did you get my point? Okay.
Yes.
Anytime we develop parallel code, at the same time, compiler also provides some optimizations. Okay, O1, O2, O3, and all those optimizations. If we consider those optimizations, okay, we can increase the speed up a lot. Okay, here when we look at this particular one, we decrease the execution time. Do you get my point? So this is the way to use the compiler optimizations. See here, actually total execution time is 9.88, right? Here total execution time is 2.4. Okay, how is that possible? That is possible. Okay, we get that much amount of speed up here by using that compiler optimization over 3. Is it clear? Okay, try to explore. Okay, there are different compiler optimizations are there. O1, O2, O3, and O fast. Okay. Suppose if you want to compile any program with such kind of optimizations, automatically you will get the better speed up. That is about events. Are you with me? Are you with me? Is there any doubt?
Yes, sir.
Okay. So here main point, suppose if you want to create an event, what we have to do is we have to declare variables to measure the uh, time of that particular event. Okay, to measure the measure timestamp of that particular event. Okay, here what I did is here I consider two variables start and stop to measure the execution time of that particular kernel. Okay, after that here I'm going to create those two events by using CUDA event create. Later, we are going to record that particular event by using CUDA event record. CUDA event record. Later, we are going to find the difference between these two by using CUDA event elapsed time. By using CUDA event elapsed time. Okay, before going to measure the CUDA event elapsed time, we have to consider one important function, that is CUDA event synchronized stop. Okay, CUDA event synchronized stop. Okay, suppose if you don't stop it, okay, sometimes we don't get the result. Okay, simply we'll get the result is 0. Okay, so we have to, before going to measure here, I'm measuring this elapsed time. Before going to measure this particular elapsed time, we have to stop that particular event. CUDA event synchronized stop. Okay, that is the brief description on this particular CUDA events. Next one is okay. I would like to discuss about streams. I would like to discuss about the streams. Okay, I think you have some idea on streams, right? You have some idea on streams, right? What is a stream, by the way? Can you give any intuition behind that? Stream is sequence of commands. Stream is a sequence of commands that execute in order on the GPU. That execute in order on the GPU. Okay, right. Here, why do we need these streams? Okay, in the last class itself, I provided a little bit introduction. Yeah, when we are working with this particular mm, simple vector dot matrix multiplication, in that context, what can be done? Here, our objective is we are going to perform dot product of these two vectors. Our objective is we, we have to we have to find the dot product of these two vectors A and B. To measure the dot product of these two vectors, okay, actually we are copying these both the vectors A and B from the host to the device. Later, here we are performing the copy operation from host to device. This is one operation is there. And next step is we are going to perform execute operation. Later, we are performing copy back. We're performing copy back from device to host. Okay. These are the steps we're doing, right? Are you with me? Are you with me?
Yes.
When we look at this particular problem, among these three operations, which one is the costly operation? Among these three operations, which one is the costly operation? Copying, actually, when we look at the execution time is a little bit less, right? But copying from host to device and copying back from device to host, that is going to take more amount of time, right? Okay, right. Yeah. Here I would like to give some little bit intuition behind that. Mm, This is simple vector dot product. Okay. Are you able to see the screen? Are you able to see the screen?
Yes, sir.
Okay. If you look at this difference between this get time of the day and this get time of the day, what can we get it? What is the purpose of the statements between those two get time of the days functions? What is the purpose of the statements, okay, between those two get time of the day functions? Forget about kernel execution. Here, I don't bother about kernel execution, right? Anyhow, kernel execution
Memory
starts.
copies. Host
Yeah,
to
yeah.
device memory.
Here, what are we doing? We are performing memory allocation. After that, we are copying that particular one from this here to there, right? Are you with me? Okay. Mm, Here, what I'm doing is that I'm going to add one more line here. That is get time of day, address of TV2, comma, PZ, PZ. Okay. Now I can comment this particular line. Okay. Suppose.
Comma missing.
Huh?
Comma missing.
Okay. Sorry. Okay. Now, actually, this particular one gives the information on actually time to copy the data from the host to the device, right? Are you with me? Are you with me? Okay.
Yes, sir.
Now, actually, when we find the difference between this particular one, so by using which one here, when you look at this particular statement, GPU memory allocation and initialization time. Okay, here it is simply copy operation, right? Are you with me? Host to device copy operation, right? Okay, yes, that particular, actually, when we execute this particular piece of code from that particular line statement, we can get some information on mm, time to perform copy, time to perform copy. Okay, here time to perform that particular copy is, what is that? How much time? See this 0.3 seconds, right? Okay, execution time. Execution time on the device is more or less this particular one, right? Here, this execution time on CPU. Execution time on the GPU is 0.08, I think. If I'm not wrong, that is the answer. How can we get that particular one? We can get that by placing that particular statement. To get the here, if we consider, if we remove this particular one, when we find the difference between TV3 and TV4, we can get the execution time of that particular device function. Yeah, now you can see this. The execution time on the device is this much. That is 0.07 seconds. and memory copy operation time is 0.31, right? Are you with me? Are you with me? Hello, are you there?
Ah, yes, sir.
Yeah. So there is a big difference, right? Suppose to actually here, our objective is we want to reduce that particular copy time. How can we reduce the copy time? How can we reduce the particular copy time?
We can do the copy concurrently, or
Yes, actually here, how many elements we're copying from the host to device? N by 2 elements, right? In this particular example,
yes.
we're copying the N by 2 elements from the host to device. After that, we are executing, right? Okay. Instead of that, instead of copying the N by 2 elements, initially we can copy N by 4 elements from the host to device. Later, we can perform the execution of these N by 4 elements. While device performing this particular execution, we can copy the remaining N by 4 elements, right? And execute it. Okay, here there is overlapping of operations, right? For the first n by 4 elements, we are performing the execution here. During that time, we are copying the next n by 4 elements. In that context, what can we do? We can save the copy time of those n by 4 elements, right? Did you get my point? Suppose, what is the concept of pipelining? What is the concept of pipelining? In
Instruction
pipe,
overlapping.
overlapped of instructions, right? Okay. Here also, we are dividing this particular operation into small operations. Okay, what are those operations? Actually, here we are copying the n by 2 elements from host to device. After that, we are performing the dot product of these two n by 2 elements. Then we will get one scalar value. We are going to copy that particular scalar value from the device to host. That is the problem. Here, what instead of working on n by 2 elements, here what are we doing here? We are dividing this particular problem into two small problems, n by 4 and n by 4. Okay. Here, what can we do? We can copy first n by 4 elements from host to device. After that, we can execute or we can find the dot product of, okay, we can find the dot product of those n by 4 elements. Okay. While performing the dot product of those n by 4 elements, we can copy the next n by 4 elements, right? Okay. That is okay, overlap execution of operations, right? Are you with me? Okay. Here, later we are going to execute n by 4 elements. Anyhow, this particular execution time is same. Okay. Anyhow, execution time of n by 4 elements, n by 2 elements, execution of 2 n by 4s, both are same. But here we are saving the time of copying those this n by 4 elements. Reason behind that is these n by 4 elements are overlapped with this operation, overlapped with that particular operation. That is why in the concept of pipelining, while overlapping execution, suppose consider a simple instruction pipeline. Okay, when we take a 5-stage pipeline and when we have n instructions, okay, suppose if there is a computer that computer don't support the concept of pipeline. In that context, to execute those n instructions, we need 5n clock cycles. Assume that uh, each stage is going to take one clock cycle. Okay. In that context, to execute those n instructions, we need 5n clock cycles. Suppose if our computer supports the concept of pipelining, okay, and that there are no hazards at all, okay. In that context, we can comfortably execute those n instructions. First instruction can be executed in 5 clock cycles. From the next instruction onwards, we can complete the execution of next instructions in within 1 clock cycle. The reason behind that is all these pages are overlapped with the other instructions. When it is overlapped with other instructions, we can save some amount of time for the other instructions. Are you with me? Are you with me?
Yes, sir.
Yeah. So in that particular context, when suppose when we consider five-stage pipeline and we are going to execute any instructions, okay, to in the non-pipeline execution, it is going to take 5 clock cycles. In pipeline execution, it is going to take 5 plus, that is first instruction, 5 clock cycles. Remaining n minus 1 instructions can be executed in n minus 1 clock cycles. Then how much speed up we can observe? 5n over this particular one. For large values of n, we can neglect these constants. Okay. So its speed up is 5n over n, that is 5x speed up. Speed up is approximately 5x. Here also, okay, if we do the overlapped execution of the kernels, or when we divide the problem into subproblems, okay, if we execute these subproblems by using GPU in overlapped fashion, we can save the time. We can save the execution time. Okay, that is with the help of CUDA streams. Okay, when we look at the definition of the word CUDA stream, a CUDA stream is a sequence of commands that execute in order on the GPU. That is the definition for the word CUDA stream. Okay, this particular stream, okay, CUDA streams provide a way to overlap computation and communication operations. Here we can overlap computation operation, that is execution operation, and communication operation, that is simple copy back operations, copy operation, that is copy from host to device or device to host. Okay. Yes, this particular CUDA streams. So with the help of this CUDA streams, supports the concept of concurrent kernel executions and concurrent memory transfers and concurrent execution of other GPU operations. That is the beauty of CUDA streams. Okay. Now take a break for a period of 15 minutes. Please come back by 7:20. Okay. Yes, in the next session, okay, I would like to give an example. How can we do that particular dot matrix multiplication by using CUDA streams? Okay. After that, I would like to discuss about how to use shared memory concept. Is it fine? Do you have any other doubts? Hello, welcome back to the session. Are you able to hear me?
Yes, sir.
Yeah, thank you. We are discussing about the streams, right? Okay. Uh, uh, you people know have some idea about the definition of the word stream and advantage of streams, right? Now I'm going to explain how can we use the streams to perform the dot product of two matrices or two vectors. When we look at this particular one here, we are working on vector dot product. First, I would like to explain dot product of two vectors by considering a single stream. Okay. Later, we can perform the computation dot product of two vectors by using multiple streams. Okay. Here, what can you see? Here you can see that just like CUDA events, here also I declared a few variables. Those variables are C. Stream 0 is a variable. That variable is of type CUDA stream. Okay. After that, we are going to create a stream. Okay. This particular stream is responsible to execute a sequence of commands. Okay. On the GPU. Sequence of commands on the GPU. Okay. Next one. When we look at this particular piece of code here, what are you going to do? CUDA stream create address of that particular variable, stream variable. After that, here, what can you see? Here, while launching this particular one, here remaining part is more or less same. Here you can find the difference. Here, what can you observe here? Instead of CUDA memcopy, here we perform CUDA memcopy async. CUDA memcopy async. Okay, what is the meaning of that? Asynchronous memcopy. Asynchronous memcopy. Okay, next one. This is another CUDA memcopy async, right? Here, when you look at this particular one, here what can you see? In CUDA memcopy async, we are passing 5 arguments. First one is the destination. Second one is the source. Third one is how much amount of data we are copying. Fourth one is the direction of the copy. And fifth one is the stream. Okay. Okay. We are performing this particular CUDA memcopy by using stream 0. By using stream 0. That means now we have two streams. Only one stream, that is stream 0. In stream 0, initially what are we doing? We are performing one operation. What is that operation? We are copying A to BA. That is the first operation. Next operation. What is the next operation? Again, we are copying B to DB. That means this is the next operation. After that, we are performing one more operation, that is sum to this one. Sum to dsum. Dsum. All these three operations are all these three uh, functions submitted to which stream? Stream 0. Stream 0. Are you with me? Are you with me?
Yes, sir.
Yeah. Now, actually, what is the definition of the word stream? Stream is a sequence of commands that execute in order. Please remember that particular point. That execute in order means that suppose if we submit all these functions to this particular stream, these statements are going to be executed in order fashion. These statements are going to be executed in order fashion. Okay, on the GPU. Later, here, what I'm doing, I'm going to calling the kernel, right? Here, when you look at this particular kernel function call, multiply using GPUs. Here, instead of 2 arguments, here I'm passing the 4 arguments. What are they? This is the number of blocks. This is the number of threads. Suppose if you want to pass some amount of shared memory, okay, here we can use this third variable. And this fourth one is a stream. Fourth one is a stream. Here we are going to submit this particular kernel call, that is multiply using GPUs. That is this multiply function to that particular stream. That means we are going to execute these 4 operations by using a particular stream, that is stream 0. Are you with me? Is there any difficulty here? Is there any difficulty here? Here what we did, okay, to perform dot product of two vectors, we had to copy vector A from the host to the device, vector B from host to the device. We had to copy sum to dsum, okay? And after that, we have to call multiply using GPUs, okay? Here what we did, we submitted all those function calls to a particular stream. Once we submitted all those function call to a particular stream, what will happen is GPU is going to execute all the function calls in that particular stream in order fashion. Is it clear? Is there any doubt? I think now you will get some intuition, right? What is the meaning of the word stream and how can we submit a set of instructions to a particular stream? Suppose, suppose if you want to submit this particular copy operation to a particular stream, here what we consider one extra argument, that is stream zero. Stream zero. That means stream zero means that these three functions are submitted to stream zero. After that, here we are calling a kernel that is multiply using GPUs that is also submitted to the stream zero. That is also submitted to stream zero. That means in stream zero, we are going to execute these four functions in stream zero. Okay, we are going to execute by using stream zero, we are executing these four functions. Are you with me? Is there any
Yes,
doubt?
sir. Yeah.
I hope that if you have any doubt, please let me know. Otherwise, I can cover the remaining points. We'll cover the remaining points. Is it clear?
Yes, sir.
Hello.
Yes, sir.
Okay. After that, here what can you see? Here you usually to allocate the memory. Suppose if you want to allocate the memory on the host machine, what we did, we considered MLR function or CLR function. Here, to allocate the memory on host machine, we consider one more thing, that is CUDA host alloc. See this, CUDA host alloc. CUDA host alloc, okay? When we allocate the memory by using CUDA host alloc, what will happen is it allocates a page locked memory. That memory is a page, page locked memory, okay? If your memory is a page locked memory, are required that page is always present in the main memory. Page is always present in the main memory. Suppose if we allocate the memory by using MLOC or CLOC, that memory is a pageable memory. Okay, that memory is pageable memory means suppose if memory is full, in that context, uh, some of the pages can be swapped out from that particular DRAM. Okay, then suppose whenever GPU needs that particular page, what will happen is OS observes the page faults, then required page will be loaded from the secondary memory to the primary memory. Okay, there is a difference between page locked memory and pageable memory. Suppose whenever we use CUDA host alloc, okay, in that context, our operating system allots, okay, a page locked memory. Page locked memory means that required page is always present in the main memory. If required page is always present in the main memory, then we can quickly transfer the data between host and device, between the host and device. That is the advantage of CUDA host alloc. Okay. Next, after that, suppose if you want to allocate the memory on the device, here we are going to use CUDA malloc. That is similar to the previous one. Next, here actually while discussing the CUDA events, actually I discussed about CUDA event record, right? Are you with me? CUDA event record. What is the purpose of CUDA event record? Any guess? What is the purpose of CUDA event record?
So
I already
when
told this.
starting and start
Yeah,
time.
it is used to record the timestamp.
Okay.
Here we are going to record the timestamp. Okay, here because we submitted all these functions to the stream zero. That is why here we consider stream zero. Next, after that, we are executing this particular function, right? That is multiply using GPUs, that particular kernel. Once we executing that particular one, here also we are recording that particular timestamp by in the variable stop zero. Here start zero and stop zero, both are the variables are of type CUDA event. CUDA event. With the help of those two variables, we can record the timestamps. We record the timestamps. When we find the difference between those two, we'll get the execution time of the kernel. Is it clear? Is it clear? Is there any doubt while understanding this particular piece of code? Nothing great. Here, when you look at this particular piece of code, here what I did is, instead of considering that particular, instead of considering default kernel, here I considered stream 0. I submitted all these functions to the stream 0. And to measure the execution time, I consider the CUDA events. I consider the CUDA events. Okay. Later, suppose if you want to achieve synchronization within a stream, okay, we can consider the function CUDA stream synchronize. CUDA stream synchronize. Within the parentheses, we have to put that particular stream. You suppose if you want to synchronize on stream 0, we have to write stream 0. If you want to synchronize on stream 1, we have to write stream 1. Are you with me? Are you with me? Yeah.
Yes, sir.
Now, after executing this particular one, what result is with d sum 0. Result is with d sum 0. Now, what we have to do, we have to copy back that particular result from d sum to sum 0. Later, we are going to print that particular result on the screen. Later, we are going to print that particular result on the screen by using the function, okay, CUDA event. Yeah, but by using this particular printf statement. Where is the printf statement? This one. Okay, we can measure the execution time of the kernel with the help. We can measure the execution time of the kernel by using CUDA event elapsed time. By using CUDA event elapsed time. Is there any difficulty while understanding this particular simple problem? Here we solve the this particular one dot product of two vectors by considering a single stream, that is stream 0. Do you have any problem while understanding this particular one? When we look at the source code, here what can you look at? Here we considered uh, a few variables, start 0 and stop 0. These three variables, that means these three statements. This statement is to declare the events. Okay, once we declare the events, we are going to create an event by using CUDA event create. With the help of these two statements, with the help of these two, we can record the execution time. We can record the execution time. Usually, CUDA events are used to measure the timestamps. Okay. After that, there is a concept called CUDA stream. Okay, CUDA stream is a sequence of commands or sequence of functions that execute in order on a particular GPU. Okay, that is sequence of statements or sequence of functions that are going to be executed in order on a particular GPU, that is called a stream. Okay, here actually for that what I'm going to do is, okay, here I'm going to consider one stream, that is stream 0. Okay, here with the help of this particular function called CUDA stream create of stream 0. With the help of that, I'm creating one particular stream. Later, what I'm going to do, okay, I'm going to submit some set of functions or some set of instructions that are going to be executed on the device. Okay, I'm going to submit set of instructions that are going to be executed on the device to that particular stream. Okay, so which statements I'm going to submit? Okay, one is that is copying A to DA. That is one function call. Okay, another function call is copying B to DB. Okay, later, okay, I'm going to execute this particular one. I'm going to find the dot product of these two vectors. Okay. Yes, these functions are going to be executed on the stream 0. Are you with me? Yes. Later, here I'm interested to find the execution time of this particular kernel. Okay. For that, what I'm going to do, I'm going to put CUDA events here. Okay. With the help of CUDA events, those are the markers, right? With the help of those markers, what can we do? We can measure the timestamps. Later, when we find the difference between those two timestamps, with the help of CUDA event elapsed time, we can get the execution time of that particular kernel. We can get the execution time of that particular kernel. Are you with me? Are you with me?
Yes, sir.
Yeah. When you look at the difference between this program and previous program, here I considered one more function that is CUDA host alloc. Okay. That means suppose if you want to allocate the memory on the host, in previous programs, we considered mloc or cloc. Okay. When we use mloc or cloc, okay, operating system allocates a pageable memory. Okay, if a memory is a pageable memory, in that context, usually uh, pages may be swapped in and out of the physical memory by the operating system. Okay, suppose if we allocate the memory by using CUDA host alloc, that is a pinned memory or page locked memory. If a memory is a page locked, okay, then that particular page is always retains in the main memory. If a particular page is always retains in the main memory, okay, then we can quickly transfer the data between host and device. Okay, that is the purpose of CUDA host alloc. Okay, that's it. Other than that, remaining statements are more or less same. More or less same. Okay, to measure that, after that, to achieve the synchronization within the stream, we have to call CUDA device, CUDA stream synchronize of that particular stream number. Okay, when you find the difference, how can we measure the execution time of this particular start and stop by using CUDA, by using this which function? CUDA event elapsed time, by using CUDA event elapsed time. Now I'm going to execute this particular one. Okay, how can I execute it? I can execute by using the command nvcc vector stream.cu minus o vector dot product stream.o. Okay, this is simple warning. Actually, we declared the variable, but we never use that. It's fine. After that, vector dot product stream.o. Here, size of the vector is 10 power 9 here. After that, 10 and 100. Why? What is the reason? Sorry, we haven't generated here. We put the C. Instead of that, we have to generate O. Yeah. Did you get here? You can see the answer, right? If we use one stream, execution time is 0.15 seconds, right? Please remember this. Execution time is 0.15 or 0.16 seconds. Now, we are going to solve the same problem. Now, we are going to solve the same problem by using two streams. Instead of one stream, we are going to solve the same problem by using two streams. Okay. Suppose if you want to solve the same problem by using two streams, what we have to do? Can you give a little bit intuition behind that? Can you give intuition behind that? You have to consider stream 0 and stream 1. We have to consider two streams. Stream 1. Are you with me? So for first n by 2 elements, we have to divide the entire work, right? Next n by 2 elements. Here we are finding the dot product. Here also we are finding the dot product. Later we are going to add these two results. This is the higher level intuition, right? Are you with me?
Yes, sir.
Okay. So with this idea, okay, we can develop the code. How can we develop the code with this idea? Yeah. Here, look at this one. Here, what I did, I considered two stream one. Later, I created two streams with help of CUDA stream. With help of CUDA stream create. Are you with me? Are you with me? Hello.
Yes, sir. Yes, sir.
Okay. After that, after that, when you look at this particular piece of code, what can you see? Here I considered uh, these variables DA0 and DB0 and DC0. When you look at the size of these DA0 and DB0, n by 2 each, right? That is for stream 0, isn't that? I created two more variables, that is two more partial arrays, that is DA1 and DB1. When you look at so when you consider DA1, 0 and DA1, with the help of these two, I can comfortably store A, vector A. With the help of these two, I can comfortably store vector B. Are you with me? I can copy half of the vector A into DA0 and half into DA1, half of the vector B into DB0, and remaining half into DB1. That is the logic here, right? After that, here what I'm going to do, when one, this codon and codon from static resonance, codon and codon. What can you see? I'm going to copy first n by 2 elements into DA0 and first n by 2 elements of B, vector B into DB0. Okay. I'm going to submit this particular copy to this particular stream 0. That means stream 0 is responsible to find the dot product of first n by 2 elements. Are you with me? Stream 0 is responsible to find the dot product of first n by 2 elements. Are you with me?
Yes, sir.
Is it clear? Right.
Yeah.
Next one. Similarly, okay, stream 1 is responsible to find the dot product of next n by 2 elements. Stream 1 is, that is why if you look at this particular one, here I'm copying A plus n by 2. Look at this particular one. A plus n by 2, that is the starting point to DA. How much amount of copy I'm doing? This is starting point. Amount of copy is this much amount of data I'm copying from this particular memory location. That is n by 2 elements. Okay. Next, actually here also we are going to copy second half of B into DB1. Okay, here which stream I considered? I considered stream 1 here. I consider stream 1. Later, what I'm going to do here, I'm calling this particular multiply using GPUs. Here I consider stream 1. Here in the previous case, I can that particular first part I consider stream 0. Now we have two streams, that is stream 0 and stream 1. Stream 1. Stream 0 works on copying on n by 2 elements. Next, execution, copying back the result. Copying back the result. The next one. Yes, one. For stream 1 also, we are performing the same set of operations. Okay. In this context, what can we do? Okay. Here, what can we do is actually we can perform overlapped execution of kernels on the device. When we perform the overlapped execution of kernels on the device, okay, we can save the time. We can save the time. Let us see. I'm going to execute this particular piece of code. How can I execute this particular piece of code? By using simple compilation. That is NVCC vector product of stream minus O stream2.o. Okay. Now, insta executable is vector dot product underscore stream to this one. This is the case. Yes. When you look at this particular one, this is the, yeah, now I'm going to execute the previous program. Previous one is the stream 1, right? Stream only, that's single stream. This is this case. Now you can find the difference. The difference is when I use the single stream, that particular stream is going to take 0.15 seconds. Okay. Here now I split that particular problem into two streams. Okay. That is stream 0 and stream 1. Now stream 0 is takes 0.1 seconds and stream 1 takes 0.78. Okay. These streams two together, it is definitely, it is a overlapped execution of instructions. When it is overlapped execution of instructions, here when we look at the execution time of this one and execution time of this one, okay? Execution time of this one is less as compared with this one, right? Here execution time is more. How much amount of less? This much, right? This is overlap execution of time. Did you get my point? Hello? Are you with me? Are you with me?
Yes, sir.
Yeah. Yes. That is the beauty of this particular one. Okay. Similarly, we can solve the same problem by considering multiple streams. Instead of one stream, we can consider two. Instead of two streams, you can consider four streams and execute it. Then also you can put a solution. Okay. That is about streams. Okay. Right. You actually in this particular class, I discussed about heterogeneous computing streams, right? If you want, you can combine both. Okay, we can create two streams. Those two streams are going to be executed on the device, and part of it can be executed on the host. If we combine all these together, we can quickly solve the problem. Okay, and that is heterogeneous computing. Instead of that, suppose if you want to solve the PGS, you can you can divert part of the problem to the FPGA, and you can execute that particular problem by using FPGAs also. Or if you want to execute it by using ASIC circuits, you can execute it by using ASIC circuits. Next one is how can we get the solution to this particular or vector dot product by using shared memory concepts. You have a concept of shared memory. Okay. What is shared memory is all the threads within a block, okay, can share the memory. Okay, then we can save the time. How can we save the time? Let us see. I would like to give a simple example for this. Here, there is a problem. There is a program that is vector dot product underscore extension dot cu. Here you can see this particular function, right? When you look at this particular function here, what can you see? When you look at the function, what can you observe here? I declared array that is cache. Okay. Size of the cache is equal to the number of threads. Okay. When we look at this prefix here, underscore underscore share underscore underscore. What is the meaning of that? Meaning of that is that particular array is shared across all the threads within a block. That particular memory is shared across all the threads within a block. If all the threads are going to share within a block, then what will happen is we can quickly solve the problem. How can quickly solve the problem? I will explain it in a minute. Okay. Here, when we look at this particular piece of code, what can you see? Before going to discuss this particular one, here I would like to this is also dot product of two vectors. When we look at this particular simple function, here we are calculating the result. Later we are performing the atomic add, right? Are you with me? This atomic add is responsible to avoid data races. Hello? 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 In the dot product of two vectors, here in this particular multiply using GPU function, here we consider atomic add. This particular atomic add function is responsible to avoid the data races. In that particular program, okay, what I'm going to do is I'm going to avoid this particular function. With the, suppose instead of considering atomic add, without considering atomic add also, we can solve that particular problem. How can we solve that particular problem? By achieving synchronization among the threads within a block. By achieving synchronization among the threads within a block. For that, okay, what I did is I considered concept of shared memory. When we declared a shared memory, all the threads within a block can access that particular memory. Later, what can we do is by using all the threads, we can perform that particular sum within a block, right? That means on here, you look at this particular problem. Are you able to see the screen? Are you able to see the screen?
Yes, sir.
Okay. When we look at till this particular point, these steps are common with the previous problems, right? Okay. Here, what I did, each thread is going to update. Each thread within a block is going to store its result to this particular shared array, shared memory array. Okay, cache of PID equal to 10. Okay. After that, what I did here, I put a simple underscore underscore sync threads. That is a synchronization point for all the threads in the same block. That is synchronization point for all the threads in a same block. That means that after executing this particular statement, where is the result? Suppose assume that after executing that particular point, this is the shared memory. This is the shared memory. For the sake of simplicity, I considered one in all the cells. Okay. Here I'm going to add all these elements by using a sum of all the elements in an array by using multiple threads. We can compute the sum of all elements in an array by using single thread execution. If we write a simple for loop, we can get it. But how can we perform the sum of all elements in an array by using multiple threads? In that context, idea is very simple. Here, what I'm going to do is when we look at this particular array, size of the array is 8, right? I'm going to divide this particular one into two parts. Okay. By using one thread, I'm going to find the sum of these two elements. By using another thread, I'm going to find the sum of these two elements. By using another thread, I'm going to find the sum of these two elements. By using another thread, I can get the sum of these two elements. Now, these sums are 2, 2, 2, and 2. We can get all these 2's in 1 unit of time. Let us assume that this particular addition can be performed in 1 unit of time. All these 4 sums are available with the help of 4 threads in 1 unit of time. Okay, later. Okay, now I'm going to consider 2 threads. These 2 threads are responsible to perform these 2 sums and these 2 sums. Okay, so within the next timestamp, we can get this particular sum, right? 4 and 4. In the next interval, we can get this particular sum, right? If you write a simple for loop, to find the sum of all these 8 elements, we need 7 units of time. When we use the concept of a parallel sum, we can get this particular sum in 3 units of time. Are you with me? Are you with me? Is there any problem while understanding this logic? Do you have any problem while understanding this logic?
No, sir, it's understanding.
Okay, I think there is a problem. I would like to close it one more time. Yeah. Now, I'm going to discuss this particular logic. That is, when each thread is going to update its value in this particular shared memory. Okay, once it is updated, this is sync point. Now all the threads wait at this particular point. Okay, after executing this particular one, okay, when all the threads reach to this particular point, this is this state of that particular shared memory. After that, we have to find the parallel sum. Okay, how can we get the how can we perform that particular parallel sum? We can perform that particular parallel sum by using this simple logic. Okay, you have some idea about block dimension.x. What is the purpose of block dimension.x variable? The purpose of block dimension.x variable is number of threads per block. Is it clear? With the help of block dimension.x, we'll get the number of threads per block. That means when n equal to number of threads per block by 2, that means we are going to consider uh, maximum loop iteration size is value is n by 2. Instead of n, we are going to consider n by 2. Now we are going to pick the thread IDs. Okay, thread ID 0, thread ID 0, thread ID 1, thread ID 2, and so on, thread ID n by 2. Okay, these threads are responsible to generate these results. Okay, later what we have to do, instead of considering n by 2 threads, we are going to consider only first n by 4 threads. Okay, first n by 4. So first n by 4 threads are responsible to generate these intermediate results. After that, what are we going to do next? n by 8 threads. N by 8 means here it is only one thread. Okay, that particular thread is responsible to generate this particular result. Are you with me? Are you with me?
Yes, sir.
Yeah. Here, this is the logic here. Okay, initially n value is block dimension dot x. That means number of threads per block by 2. N value equal to n by 2. Okay. After that, here what can you see? If thread ID is less than n, that is thread ID is less than n by 2, do this. Here, what is that? A cache of TID equal to cache of TID plus cache of TID plus n. That means if TID value is 0, thread ID is 0. Next to 0 plus, here we already computed n equal to n by 2. Okay, 0 plus n by 2. That means this particular thread is responsible to perform the addition of these two quantities. And next thread, TID equal to 1. That thread is responsible to perform the addition of these two quantities. And so on. Okay. Yes, if we repeat that process, at some point, we can get only one thread. Okay. That means when should we come out from this particular for loop? This particular while loop, we come out from this particular while loop when n value equal to 0. If n value equal to 0, that means that particular sum of all elements of that particular array is with this first cell. Okay, is with this first cell. Then we are going to copy back one into the appropriate block index. Okay. Now, okay, with that idea, I would like to discuss code. Just to go through it. Okay. Here, what I'm going to do is I want to find the dot product of two vectors by using the concept of shared memory without considering that particular atomic add. What I'm going to do? I'm going to read size here. That is size, right? So based on that value of the size, I'm going to allot the memory for A and B. Here we don't need this particular one. C. Okay. Okay. Right. Next one is when we look at this particular array of income, probably, we are going to initialize these two vectors with some values. Later, with the help of CUDA malloc, we are going to allocate the memory and the device. Okay. Next one here, by using the concept of shared memory, what is shared memory? All the threads within a block can access that particular memory. That is why that is called a shared memory. That is why here we are considering one array on the device DC. Size of that particular array is equal to the number of blocks. Size of that particular array equal to the number of blocks in that input, right? How do we calculate number of blocks? Okay, you have some idea to calculate the, okay. Next one is here. When you look at this particular one is CUDA and copy. These two functions are used to copy the data from host to the device. Once we copy the data from the host to device, what can we do? We are going to call the function multiply using GPUs. Okay. Once we perform multiply using GPUs, here this is responsible to multiply the dot product of two vectors. In that context, where is the dot product? Suppose here we solve this particular problem by submitting this by considering this particular configuration. Here number of blocks is suppose consider number of blocks is 4. So now we have 4 blocks. This is block 0, block 1, block 2, block 3. This is one temporary result is with block 0. This is temporary result 1. Another temporary result is with block 1. Another temporary result with block 2. Another temporary result with the block 3. Okay. Yes. Where are these the 4 temporary results? These 4 temporary results with the array DC. Okay. Later, what we have to do? We have to copy all these temporary results from, okay, this one, device to the host. When you look at the direction of the copy, this is the direction of the copy. We are going to copy that results from the device to host. In actually on the host machine, we are performing this particular sum. If you want here, you can use the OMP function called hash pragma OMP parallel, okay, for and perform the reduction operation and sum. Reduction operation and sum. Are you with me? Are you with me? Is there any doubt? Okay, now I'm going to execute this particular one. Now I'm going to execute this particular one. How can I execute this particular one? I'm going to execute by considering NVCC minus O vector dot product extension dot O. Dot vector dot product extension dot O. Size of the input is 10 power 9. This is 10 power 8, 10 power 9. Number of blocks is 10 and the threads per block is 100. Yeah. Here you can see that execution time on the device. Execution, that means we can quickly compute the results by using within 0.05 seconds, right? Okay. Suppose if you don't consider this one, okay, if you don't consider the shared memory, then execution time is, see, here we have results, right? Vector dot product. Yeah. Here, when we look at this particular one here, you can see that this is the half of the execution time on the device. This is the remaining half on the CPU. Both together, it is going to take, okay, 0.24. Here we can solve the same problem in 0.05, right? Well, that is the beauty of shared memory. Here we are performing that particular, actually here we consider atomic add, right? Okay. Here what we did, instead of performing atomic add, we reduced to, actually we are performing that particular reduction by using the shared memory. How can we, that means we perform that particular parallel sum using the concept of shared memory. Okay. Here, what is shared memory means, here we are going to declare a shared memory. What are we going to do? We are going to use a simple syntax, that is underscore underscore shared underscore underscore. That is the prefix we are going to use, right? After that, given data type and cache of that particular num threads, right? That particular size of the shared memory. Okay. That is the beauty of. So when we declare a shared memory, what will happen is this shared memory is local to a block. All the threads within a block share that particular memory. Okay. So based on that only, here we wrote the reduction logic. By using this particular reduction logic, we can reduce the execution time. So when you look at this particular CUDA, what we discussed in this particular CUDA, okay, we discussed about simple architecture, CUDA architecture. After that, we discussed about simple programs. How can we write basic CUDA programs? Later, we discussed about how to calculate dot product of two vectors and how to perform the multiplication of matrices. Okay. After that, we introduced the concept of heterogeneous computing. Later, to measure the execution time of the kernel. How can we measure the execution time of the kernel by using CUDA events? Okay. Later, we can solve the problems by using the streams. Suppose if we use the concept of streams, it supports the concurrent execution of the kernels. When we consider the concurrent execution of the kernels, we can save the time. we can save the time when we overlap the operations. Okay. After that, we discussed on shared memory concepts. How can we use the shared memory programming in CUDA? Okay. Due to the lack of time, I was unable to cover that particular kublas. Okay, and thrust library. Whenever we have a time, please go through that kublas and thrust library. That is very simple and straightforward. Those are the built-in functions are there. With the help of those built-in functions, we can perform certain operations in less amount of time. Right. That's it. That is the end of this course. Do you have any doubts? I'm here to clarify your doubts. Okay.
Sir, can you share this program, sir? This
Yeah,
examples
definitely. I will
program.
share these programs with you.
Okay. We will run in our local machines.
Yeah, sure. By today night, I will share all these programs with you.
Oh, thank you, sir.
Right.
Thank you so much for your sharing valuable
Next.
time.
After that, would you like to give any feedback?
Thank you, sir. So we learned the basics. So actually, we have to practice more actually, because since yeah. So CUDA and other basics are very interesting, sir. Actually, so earlier we thought once these are some of the things are new to me. When we compile CUDA program, we are getting two executables actually. Literally, conceptually it's two. So one for GPU and one for CPU.
Okay. Other than that, what else we expect? What else you expected from this particular course? Did we miss anything, or would you like to suggest anything else?
So this is mainly focused for application developers. So since I'm from administration,
Okay.
so like how to provision HPC, cluster managers, those things actually we are very much interested, because
Okay.
day to day we are dealing with
You're looking for cluster management
scheduler, yeah, scheduler and
from system administration point of
system
view.
administration point of view.
Okay, that is good. Good feedback. Okay, most probably the next session. Okay, in future, most probably we'll cover that particular.
And this actually now CentOS is obsolete for HPC. So
Pardon?
CentOS is not there. Support is not there.
Okay.
So we are focusing on the Rocky Linux only for HPC.
Oh, okay. What are the advantages with the help of Rocky Linux?
So it's free, and it's open. HPC also supports Rocky Linux.
Okay.
Because otherwise we have to go for Red Hat, and that is payment basis.
Okay.
So Rocky Linux actually they have six tools actually.
Okay.
Rocky actually that company CIQ they have six tools actually. One is
Okay.
Rocky Linux, the OS part, and other
Okay.
is Aptainer, like Singularity container.
Okay.
They renamed the Singularity only Aptainer.
Okay.
That is equivalent to this container applications.
Okay.
Then Ascenter is there, that is equivalent to Ansible.
Okay.
Then Werewolf actually it's a cluster provisioning tool.
Okay.
And then Mountain, some cloud based tool is there, and Fuzzball for federated HPC and other things are there.
Okay. No. Okay.
So,
Actually, is it possible to share that document with all the participants? Can
this
you
is available, sir.
prepare?
CIQ. Yeah.
Can you prepare a little bit small document on the system admin point of
Tools.
view?
Okay,
Okay,
okay, sir. Okay.
and share with all the participants. It will be useful to all the participants, right?
Okay, sir. Okay.
That is,
So you want what are the tools
yeah.
like that?
What are the tools? What are the latest tools in that particular area?
Okay,
Okay,
okay, sir.
which one
Okay.
is best? Okay, what may be
Ah,
the reason for that? Give a brief introduction, not too much. At least two or
okay,
three
okay.
page document that is more than sufficient.
Okay, okay, sir. Okay. Actually, I'm going through that SC23 videos.
SC23 videos. Okay.
Scientific Computing 23 videos in
Okay.
YouTube. So they're actually CIQ, Rocky Linux, their stalls actually in AC23, that stalls. So wherever, so they are displaying their products and discussing those things.
Okay. Okay.
So actually, now HPC they are moving to cloud. So then we have to containerize all the applications. So how to containerize the install? How to make the application containerizable?
Okay.
So those things actually we are doing something.
Good. Okay. Else? Anyone else? Can you share your feedback or can you share the suggestions? Do you face any difficulty while delivering the lectures, while understanding the concepts? I'm happy to receive feedback from you because virtual environment is it is a kind of different environment for right. Okay. Thank you. We need to practice concepts ourselves more. Okay. Good. Thank you. Thank you very much. Okay. Thank you very
Thank
much
you,
for your
thank you, sir.
patience.
Thank you for all your efforts. Actually, so actually you put a lot of effort. Actually, so we need to do
No, no.
some homework.
Anyhow, right. My actually point is we have to be good at HPC concepts. The reason is
Yes,
that single thread programming is obsolete now.
yes,
No one will in future. No one will consider single thread programmers, right?
mm.
We have to be multi-core programmers, right? Or many
Yes.
core programmers.
Here
That is the
still,
need.
here still people are using CPU cluster only. GPU one or two nodes we have in the 40, 50 node cluster, but very less people are using because their code is not already. It's still in CPU. The code
No,
is not
no,
changed.
no. Here, one more difficulty is to use the multi-core software or many core programming. Some people should have some idea on architecture, right? Without architecture,
Yes,
they
sir.
cannot write efficient codes.
Correct, sir.
Yeah, that is the main bottleneck here. Okay.
Yeah, architecture also keep on changing. So
If the architecture keep on changing, actually, if you know the architecture, then only we can write the better codes.
yes, sir.
Yeah, that is the one important point.
And mathematics
I think
behind
you are
the
working for
HPC.
ICER, right?
Nicer, sir. Nicer Bhubaneswar.
Nicer Bhubaneswar, right? Where is it?
Yes.
Nicer in Bhubaneswar itself, right?
30 kilometers from Bhubaneswar airports.
Okay, okay, good, good.
It's actually a DAE organization.
Okay, DAA organization. Okay,
Yes. ISER
okay.
format only. It's a NISER, National Institute of Science Education Research.
Yeah, if there is any possibility, we can conduct a little bit workshop for your employees.
Yes, sir. Yes, sir. Here actually we have students, sir. Actually, here actually students, our HPC users are around 150 HPC users are there. Students they are using, sir.
Okay, okay, okay,
So we have 97 node HPC one and 40 node HPC and many small HPC grade servers we have.
okay.
So we use XCAT cluster manager for provisioning and other management, and Slum
Okay.
scheduler for fast
Slum is
share and
important. Yes, that's true.
so Slum. I also conducted some workshops, in some
Yeah.
colleges.
Okay.
Slum,
If possible, what can we do is actually you can organize 1 day or 2 day workshop for your
yes.
employees or students. Okay,
Okay, okay,
we can collectively do that. I think
okay,
in that
okay.
suppose when we do this particular one hands-on experience and all those things, right? Not
Hmm.
virtual kind of.
Yeah, yeah,
If you
yeah.
do the
In
physical
person. Yeah,
workshop,
yeah.
then students will be benefited a lot.
Yes, sir. Yes.
Hmm?
Yeah, yeah. We will do.
Try to do that. Actually,
Yeah, yeah.
thing is try to spread the culture of HPC programming.
Yes, sir. Yes, sir. Yes. We will do
Okay.
it.
Next, actually, I received one question. One question on the use of GPUs. Vendors try to push AMD CPUs plus GPUs, while some suggest using ARM plus NVIDIA. What do you suggest? How much
Maybe
effort will be required to port the code in both the cases? No, thing is very clear, right? When we look at this particular GPU programming, if you know MPI and GPU programming and MPI both are more or less similar. Actually, here we change a little bit functions, right? Similarly, when we move from CUDA, that means CUDA to the heap programming, almost majority of the functions are same. Only we are going to change the function names, right? Just like that, suppose if there in future, if someone comes up with some other, we can easily learn that particular programming language within the span of 1 week, not more than that. If you know any one of the programming languages, right, that means any one of the parallel programming languages, we can quickly learn any other parallel programming language within a week. If you know the sequential programming, either if you are good at either C++ or Java, you can learn any object-oriented programming language within 3 days. We should know how to use those object-oriented concepts in that particular language. If you know the syntax of that language, we can straight away, we can use it. Along with that, we should have some idea about those compilers and what are the options are available with those compilers and what kind of intermediate code it generates. If there is any possibility, how can we optimize that particular intermediate code? That matters a lot. Suppose if you are able to combine, if you are able to edit the low-level code, then we can find good opportunities to get the better speed up. Compiler generates some code, right? If you are able to if you are able to optimize intermediate code, then we can write the better programs as compared with this high-level programs. Yes, Rishikesh. Any other questions? If there are no more questions, thank you. Thanks a lot.
Thank you, sir.
Okay. Thank you.